Great. So I'm Roger, and I want to present a bit of recent work that I've been doing with Stephen, Will, and George on likelihood approximations and simulation-based inference from large-scale CMB data. And it's great to see that these in-person formats are happening again. Unfortunately, I can't be there since I'm still stuck in Europe. But yeah, looking forward to meeting you all in person perhaps soon. So first of all, why do we need likelihood approximations? So the CMB, if we look at smaller scales, is quite Gaussian. All the Gaussian likelihoods work extremely well. We can very nicely extract the information. But when we go to large angular CMB scales, we are noise and systematics dominated in polarization, and we don't have an exact analytic likelihood. And we have quite a limited number of simulations. So that's quite a kind of a big problem to deal with. And the physical motivation in looking at large angular scale CMB data is twofold. So one is we can constrain the optical depth to reionization tau, which is a measure when stars first began forming and reionizing the neutral gas in the universe, which is very relevant for the sum of neutrino masses AS, NS, sigma 8. And on the other hand, it's important when measuring primordial gravitational waves parameterized by the scalar to tensor ratio R. Today we'll focus on the optical depth parameter, but the procedure can be used in the same way for R. And our approach was then to do an improved noise and systematics modeling, to have noise covariance matrices that capture systematics and use those in order to compress the data and then make unbiased inference using two different classes of likelihood methods. One is a maximum entropy-based methods, which is a semi-analytic approach, and the other one is simulation-based likelihoods. So since this is a simulation-based likelihood session, let's first summarize what is going on there. So we take the CMB maps, we degrade them to some resolution to make them computationally feasible, and then we compress our CMB maps down to some summary statistics. Here we use the power spectrum, but in principle, one could also use neural network-based compression and other forms of compression. Now we know the parameter that we're interested in general called theta, is tau in this case, and our model varies as a function of tau. And then we generate mock data in pairs with these different realizations of our tau parameter to train our models. And we want to get out the posterior density given by Bayes' theorem at the end. Now, before diving into the technicalities of our approach, let's have a look at the data first. So on the left-hand side, you see power spectra for the largest angular scales of the CMB, so the lowest multiples, 2 to 30, for temperature and polarization. So TT is temperature, TE, EE, BB, the polarization cross spectra. And the black line gives us a theoretical power spectrum with a realistic value of the optical depth parameter of around 0.06, given by the Planck collaboration. And in blue, you see a very high value of tau, and in red, a very low value of tau. And the gray shaded area is the uncertainty coming when measuring the cross spectrum on the actual data. This is the uncertainty you get. So you see that TT and TE is not very constraining on their own. However, EE, you can constrain the optical depth parameter. So the novelty here in this approach was first to do a joint likelihood of temperature and polarization. So have TT, TE, EE, which can be extended to also accounting for BB, EB, etc. And then to use novel likelihood approximations or simulation-based likelihoods. And on the right-hand side, you still have the theoretical line shown in black to guide the eye, but in blue and red, you see the Planck 2018 data or the SROL2 data, which is just an updated map-making algorithm of the Planck 2018 data, and the cross-spectrum measurements. So you see these points jump around quite a lot, which comes from them being systematics and noise dominated at these large angular scales. So how can we make unbiased inference using this very noisy data? So therefore, we will use two classes of likelihoods. On one hand, we'll be using the simulation-based likelihoods called SimBal and Delphi. And on the other hand, we'll use an approach called GLASS, based on the principle of maximum entropy. So the main difference, as said earlier, is that one is simulation-based likelihood, and the other one is based on analytic approximations to build up a sampling distribution. So let's focus on the simulation-based likelihoods first. The key assumption here is that you have some functional form which describes well the distribution of the cross spectra of your data or your simulations. So you generate a large suite of simulations, measure the cross spectra on all of those, and then you fit in the most basic form, the SimBal approach developed by the Planck collaboration, a third order polynomial to this distribution. And then from this polynomial or this fitted function, you can evaluate it at the power spectrum of the data and then build your log likelihood or your likelihood from it, called C-SimLo. A generalization of this is the Delphi approach. So this was developed by Justin Altsing and others, which is called the density estimation likelihood free inference. I wouldn't call it likelihood free, but much rather a simulation-based likelihood, which is based on the same idea, however, being a bit more general. Here, the idea is that you can fit a family of functions to the distribution of spectra and then make unbiased inference as well. Here, you use a neural network to do this procedure. So you measure your power spectra on the simulations, you find a mapping from your power spectra to some Gaussian distribution, and then you sample from this Gaussian distribution multiplied by some Jacobian transformation in order to get your posterior. This is then called a normalizing flow, and the implementation will be called PyDelphi. And the second class of likelihood is called GLASS, based on the principle of maximum entropy. And what is interesting is you don't need any additional simulations except the ones that you need for your noise covariance matrices, which you need anyway to compute the power spectra. But you compute the moments of your data analytically. And from the moments of your data, you then can approximate the sampling distribution. And the sampling step works in such a way that you integrate from some fiducial model to a theoretical model to get a change in parameter space or in your log likelihood. And this then is called memento. So these, now we've set the stage, and this sounds all quite nicely, but do they all work? So on the left-hand side, we do test these three methods on simulations. So each black line is a posterior for one realization of the sky with realistic noise and systematics. And we see just by eye, they all agree quite beautifully. And we have an unbiased estimate of tau. The input tau was 0.06 on all three methods and quite similar error budgets. Now what we wanted to see is, do all three methods pick up the same information, since they all use the power spectrum as input data and then try to constrain using the power spectrum. The green crosses here are the scatter plot between the SimBal approach and the PyDelphi approach, so the generalized version of the SimBal approach. And you see that you have a perfect correlation and both basically extract the same information. However, if you compare the maximum entropy approach to the simulation-based approach, you see a bit of scatter, and that's quite interesting. So it looks like we're extracting different information using different methods. And that's something we're trying to better understand at the moment, which method picks up which information and why. So I've said earlier that we're doing a joint likelihood for temperature and polarization. So looking at them individually, you get the EE posterior from the dashed line, less constraining the TE, and least constraining the TT posterior. And combining all three, you get the red posterior and quite a nice constraint on tau. However, problem with simulation-based likelihood is that when you have quite a high dimensional problem, as in this case, 3 times 30 multiples, so roughly 90 dimensional problem, you need additional compression. And this additional compression leads then to loss of information. So here, what we do is this compression is just taking the 30-dimensional power spectrum vector for each cross spectrum, score compressing it to one parameter, and then using these 3 resulting parameters in order to constrain tau. And we see that our posteriors widen again by 10% compared to the uncompressed case. So this compression versus no compression case, we did it on a lower dimensional problem in order to see if we kind of how much information we lose. So now exploring the whole cosmological parameter space, what is the science output of all of this? So using these novel approaches, the maximum entropy approach, we can tighten our posteriors by more than 30% and have a very robust way to infer the optical depth parameter. And this approach is then interesting not only to analyze the optical depth parameter, but for upcoming surveys such as Lightbird for the CMB case, but also for, to measure R, but also when going to Lyman alpha, for example, where we have highly non-linear flux field to make inference. And the only thing you need for the maximum entropy case is a sufficient statistic, which is the big advantage of it. And then you can analytically compute or approximate your sampling distribution. The big advantage of the simulation-based inference, however, is that you're not only restricted to using the power spectrum as an input, you could use any compression of your data. And that's something I'll be exploring with Will and Shirley in the near future. What happens if we use neural network-based summary statistics instead of power spectra? And can we extract more information from cosmological data sets? So yeah, I'll be happy to take any questions, and I'll be applying for postdocs this fall as well. So I'll be also happy to chat with some of you regarding that. Thank you very much.
Thank you, Roger. Should I be talking here or should I go there? Okay, so thank you, Roger. Questions for Roger? Chan. Yes.
Oh, wow. Okay. Hi, Roger.
Hi,
thanks for that great talk. I have, in the comparison you did with the score compression and the uncompressed power spectrum, were both of the posteriors derived? So both of the posteriors were derived from pi Delphi. How can you be sure that the uncompressed one, which is a higher dimensional density estimation problem, is accurate?
Good question, thanks. So what we did here is instead of taking the full problem, we restricted our multiple range. So instead of taking 3 times 30 multiples, we took only the most constraining 10 multiples. So the optical depth is basically constrained using multiple 2 to 10. And there we then have a 3 times 10 dimensional problem, which is a 13-dimensional problem where we know what the result should be. So we took a case that we know worked using pi Delphi.
But is there like an independent validation of the posterior that you did for that, for the 30-dimensional case?
So for the 30-dimensional case, this is what we did then using Memento. This is then the maximum entropy-based case. And for the pi Delphi case, we took also only using polarization data, one 30-dimensional problem. And all these different posteriors agreed quite nicely with each other. So that gave us confidence that comparing the compressed to the non-compressed version is actually giving us sensible results.
Great, thanks.
Any more questions? Oh, yes, please.
Hi, my name is Ira. So if you go, well, you don't need to go to slide 5, but it's there. So the maximal entropy principle, I'm wondering, right? So maximum entropy only occurs when a system is fully thermalized, basically. So does that mean that what you take here in the glass approach is just kind of a end states, slices of end states of different, let's say, processes?
Yeah, thanks for the question. That's intuitively, that's how you could look at it, yes.
So it's possible that several, I don't know, let's say, fast occurring or rapidly occurring processes gets, I don't know, ditched by the wayside, in a sense. I'm not sure about this myself, so there's no.
Yeah, that's an interesting question. To be honest, I haven't thought about it in depth before. However, I think this doesn't mean that the approach is wrong. I think the only consequence this would then have, that your exploration of the parameter space will take longer, since you might since you're integrating from some fiducial model to some theoretical model to explore your parameter space, and you might then take deviations instead of quickly converging to your maximum likelihood point. I think that's how I would see it.
Yeah, so, but the noise covariance metrics would be then even noisier, let's say, than it would be if you're just looking at end states.
Yes.
Okay, good. Thanks.
Thanks.
You have a question? So Shirley.
Thank you, Roger, for the talk. Just a very generic question. Have you found anything surprising in your endeavor comparing all these different likelihoods? And do you expect any challenges when you cannot just use power spectrum as input?
Yeah, I think two things. So one is when looking at simulations, how both methods work. So what is quite surprising is that although the correlation seems to be quite nicely between the maximum entropy and the simulation-based case, they're both picking up quite different information, and we haven't fully figured out what it is exactly that they're picking up, or what is the difference that they're picking up. Because when you see here, one is picking up quite a low value of tau and the other one quite a high value of tau when comparing a maximum entropy to a simulation-based case. So that raised a few flags with us. And that's something we're trying to better understand. I think the second part of your question is going beyond the power spectrum will be a very interesting question. So and that's why I think is the simulation-based inference is very interesting. So can we extract more information by using some neural network-based compression in comparison to the power spectrum? The power spectrum works quite well, and we can constrain a lot of parameters with it. But when going to large-scale structure, perhaps we could even extract more non-Gaussian information by using a different summary statistics. And I think that's where a natural extension of this project would be very interesting.
Thank you very much, Roger. I think we need to move on. Are you the next one, Chan? Or? Okay, so thank you, Roger. You are now in person, I guess, no? So Chan, if someone doesn't, I mean, it's maybe if you can introduce quickly yourself, so everybody.
Sure. Testing. Okay, great. Hi, everyone. My name is Cheng-Hoon Han. I'm a postdoc at Princeton. And today I'm going to talk to you about how we can use higher order statistics and simulation-based inference to improve our large-scale structure analyses. So since it seems like a pretty diverse audience, let me give a very brief primer on large-scale structure. You have a big telescope here, like DESI. Not all of my texts are showing. Oops, sorry. Like DESI here, it collects millions of spectra of galaxies. We get redshifts from those galaxies to get a three-dimensional distribution. And then from that, we calculate the cosmological parameters. There was more, but they got cut off. So effectively, our job is sort of a glorified data compression. We're taking all these millions of galaxies and then compressing them into a few numbers. Okay, so the standard analysis that's done in large-scale structure is Bayesian inference with two-point statistics, such as the galaxy power spectrum. So here's Bayes' law, and half of like my equations are not showing up. there any way to, sorry? Yeah, there should be two.
One second.
No. It's just like in the future, if half my slides are missing, it might be a little confusing for me. Yeah, I'll try to go ahead. Okay, so if it gets worse, I'll try to go with that. It was just the likelihood, okay? The likelihood is where all of our cosmological knowledge comes in with the observed power spectrum measurement and the model power spectra and all that. But there's a number of limitations to the standard analysis. First of all, the analytic models are based on perturbation theory, and they are inaccurate on nonlinear scales. So this is a plot from a recent paper from Anton and Misha that shows the theoretical uncertainties as a function of k for the power spectrum multiples. And you can see that as you go to higher k's, the uncertainties really expand. So we're losing a lot of constraining power there. Furthermore, a lot of the observational systematics that we have are currently corrected in the measurement themselves, but those are quite difficult to correct oftentimes. So this is looking at the residual of the power spectrum monopole with the nearest neighbor correction already applied. And the gray area is the cosmic variance. And you can see that for k greater than 0.1, the effect is already larger than cosmic variance. So this is already a problem. And another limitation is that the likelihood is not Gaussian, as Roger mentioned before, anywhere outside the limits of central limit theorem. So this is kind of an extreme example from Roman's paper back in 2000 with the IRAS survey, which had a whopping 4,500 galaxies. And this is the distribution of the power spectra. And you can see clearly here, comparing to the black Gaussian, that the distribution is very non-Gaussian. And last thing I want to mention is that the current analyses focus on 2-point statistics. So they're really not including any of the constraining power beyond the 2-point. So this is my favorite example to go to. Here are two very, very different distributions by I. They have the same power spectrum, the red and the blue there. Of course, if you look at any of the higher order statistics, you can immediately tell they are very different. Okay, so I want to first focus on the two of the things that I mentioned, which is that we don't exploit the constraining power in higher order statistics and nonlinear regimes. So, whoa. Okay, now I'm missing slides. Oh, well, anyway. So the question that I want to answer is then, what is the total information content of the higher order statistics on nonlinear scales? In other words, what is the standard analysis missing out on? So to answer this question, Paco and I, we created the Molino suite. It's a suite of 75,000 galaxy catalogs that are built on the Quixote M-body simulations. And it provides the two key ingredients for quantifying the information content of any galaxy observable. It has 15,000 M-body simulations, so you can estimate the covariance matrix, even for something as high dimensional as a bispectrum. And it also provides 1,000+ simulations for each parameter so that you can estimate the derivatives for the 6 cosmological parameters plus the 5 HOD parameters. So it provides everything we need to quantify the total information content of the redshift space galaxy bispectrum to nonlinear scales. So here's the result of the forecast. Here in blue is the forecast for the power spectrum multiples down to k of 0.5, so down to nonlinear scales. In blue. And then in green is for the bispectrum. And then in orange is from the joint power spectrum multiple and bispectrum. Now, you can clearly see that including the bispectrum dramatically improves all of the parameter constraints. And if we focus a little bit more onto the cosmological parameters, only in the top, then you can see that for omega matter, omega baryon, H and S and sigma 8, the constraints are 3 times tighter than the galaxy power spectrum alone. And for the neutrino mass, it's over 5 times tighter. And this is looking at the constraints as a function of K max. And what I want to emphasize here is that there's significant amount of constraining power coming from nonlinear scales. So you can see that the sigmas decrease continuously as you go from left to right. So hopefully that's convinced you that there's a lot of constraining power in higher order statistics and nonlinear scales that's not exploited by standard analysis. Next, I want to talk about systematic effects. So I showed this plot before about the effect of fiber collisions on the power spectrum. Fiber collisions is this observational systematic on the focal plane. There are corrections, including the work I did for this, which improves it for the power spectrum. But they all come with some caveat. And more importantly, fiber collisions doesn't just affect the power spectrum, it also affects any other observable you can have, including the bispectrum. And in the bispectrum's case, it's a shape-dependent imprint. I need to update this figure. This is the ugly figure. But and right now, there are no correction schemes available for higher order statistics. Fortunately, though, what is hard to correct in the measurement itself is relatively easier to correct in the forward model. So the footprint completeness fiber collisions, we have all the technology to simulate these things forward. And as a demonstration, here's a mock BOSS low Z sample constructed from the Quixote M-body simulations. And in the legend shows the progressive level of realism that I'm applying to it. So black is when you take the M-body simulations, remap it, make the light cone, and then apply the survey geometry. Blue is when you apply the veto mask to get those little holes. And then orange is now when you apply fiber collisions. And all of that takes about a minute. So it's not a very computationally expensive task. And here's a comparison with the actual data, and you can hardly notice a difference. So the last thing I'll talk about is the incorrect assumptions on the likelihood. So I showed this figure before, and you might be thinking IRAS is from like 1980s. It's 4,500 galaxies. Like now we have millions of galaxies. Is this still a problem? And the short answer is yes. In my recent work, we looked at the power spectrum multiple analysis for BOSS from 2017. And this is a comparison of the posterior. Orange is the standard Gaussian assumption likelihood, and blue is the standard Gaussian assumption likelihood, and orange is the a more accurate estimate of the likelihood. And for F sigma 8, you can actually see there's a significant like 0.4 sigma difference between the two. So it is already an effect. And even less sophisticated than that, if you were to just take the bispectrum, look at one of the bins and look at the distribution and then compare it to a Gaussian, you can very easily see that it is not a Gaussian distribution. And this is with pretty broad bins, so it's including a lot of triangle configurations, and that this is still the case. Fortunately, though, assuming a Gaussian likelihood is completely unnecessary because of simulation-based inference, also known as likelihood-free inference. And Roger talked about it before, so I'll be brief. It makes no assumptions on the functional form of the likelihood, and it can be used for any observable we can measure in the observations, which is a big advantage. So I'll be very brief. So like just to give an intro on SBI, consider a 1D parameter space and 1D observable space, and some model that generates the observable from the parameters F. Okay. If you were to draw many, many samples from your prior, evaluate the model, and so those X points there, and then you were only to keep the pairs where the observable is close to the observations, and you throw out the rest, then you have the posterior, and you've also just done simulation-based inference with approximate Bayesian computation. That's all there is to it. It's that easy. Of course, in reality, it wouldn't be one-dimensional and one-dimensional. You'll have some observables, such as the bispectrum, which is much higher dimensional, and the cosmological parameter space is also higher dimensional. And your model or simulation would be an n-body simulation, which is expensive to do. So it would be much, much more expensive. But it's possible. I did it with HOD analysis with population Monte Carlo, but I would not recommend it. And mainly because there are new density estimation techniques in machine learning that are making SBI much, much more efficient. So one example I want to give is my recent work where we used the independent component analysis to estimate the likelihood distribution for a 37-dimensional power spectrum likelihood. And based on the KL divergence, this is the KL divergence distribution here, comparison, our likelihood estimate was more accurate than the Gaussian pseudo likelihood, which as I call it. And this was done with only 4,000 simulations. Then there's also new methods like the one Roger talked about, Delphi by Justin Alsing, that uses neural density estimators to estimate the joint distribution of theta and x. And then afterwards, you can sample that distribution to get the posterior. Most recently, I've been interested in conditional normalizing flows, such as masked autoregressive flows, where you can estimate the posterior conditional distributions directly, which means you can estimate the posterior directly. So I'm not going to go into details about normalizing flows, but you're learning a mapping from a Gaussian distribution to whatever distribution you want. Because of the autoregressive structure, you can actually exploit it, make it conditional. Got it. And so recently, Digvijay and I, we did this comparison to really see if we can use conditional normalizing flows to accurately do parameter inference. So Jay nicely provided me with a whole bunch of samples of the power spectrum, like 120-dimensional power spectrum. And then I trained a CNF with 5,000 samples, just 5,000 samples, and compared it to the actual distribution. And as you can see, it does pretty well at reproducing the orange versus the black distribution. It does pretty well at reproducing the full posterior, even with a limited number of samples. So here's my summary. So higher order large-scale structure statistics and SBI can exploit the substantial power, constraining power in higher order statistics and nonlinear scales. 3 times tighter constraints on omega matter, omega baryon, H, NS, and sigma 8, over 5 times for neutrino mass. With the forward modeling, it's very easier to account for observational systematics. And with SBI, you can relax all of your assumptions on the likelihood, and you can do this with just thousands of simulations, which is the current budget of large-scale structure analyses for estimating the covariance matrix anyway. And hopefully the next time you hear from me, I'll be presenting results from SimBig, simulation-based inference of galaxies. We chose it because it has the word big. And this collaboration, we're going to be analyzing the BOSS bispectrum and other observables with SBI. And then afterwards, we'll move on to DESI and PFS. I can take questions.
Questions for Jan? Yes. There you go. Yeah.
Yeah, thank you very much for the interesting presentation. So I've had 2 questions. One is how these likelihood-free methods perform on the tail of the distribution. Because to me, for example, the risk of having a wrong likelihood is mainly at the tail, but not at the core. Like if you have a 0.5 shift in the core, it doesn't matter very much. But when you have a 3 sigma discrepancy, you really want to know whether the likelihood is Gaussian or not. Yeah, so I wonder how these methods perform on this.
So I think I still need to do a more concrete examination of that. But from my experiences with the posteriors that I've shown you so far, it's done a remarkably good job at capturing the entire posterior. And for instance, the independent component analysis method that I was talking about, for that, we actually quantified the KL divergence. between the true likelihood and our estimates, and we do better than the Gaussian estimate. So I think for that, for instance, it's pretty conclusive that
okay.
Better.
And my second question is about could you provide some intuitive understanding of why these methods work better? Like we have a high dimensional distribution and we want to characterize them. So kind of the covariant matrix is using one way of parameterization and with some number of free parameters. And here, like, so my impression that in the neural network, we have much more free parameters to fit, but kind of why it works better, why it's not overfitting.
Well, so I think, let me first address why it's better. I think it's better because the Gaussian is actually not likely, the likelihood is not Gaussian, is not actually Gaussian in many, and I've shown you some examples of that. So assuming that it is, and then fitting a covariance matrix and doing that, we know that that's not the right thing to do, or we know that that's inaccurate at some level. So I don't think it's a surprise that other methods that estimate the density more accurately, that there would be other methods that estimate the density more accurately. And in terms of overfitting, I mean, each of these methods that I showed, they have, this is not like a new problem. This overfitting is also a concern with many people who are using these methods. So a lot of these methods have their own ways of making sure that it's not overfit.
Okay, thanks.
Any other question? Okay, please.
I have a quick question about how much does it matter to have like fiduciary cosmology crack for this kind of simulation? Can you do this simulation-based inference at fiduciary cosmology, but still get the relatively correct result, or do you have to keep generate simulation? And
so if you do it at the fiducial cosmology, which is what I did for the ICA example, because you're fixing the cosmology, you're just getting the likelihood, you're not getting the posterior directly. So I think then it will matter that what fiducial cosmology you choose. And in fact, studies of the covariance matrix's cosmology dependence, there is some cosmology dependence. So I think for sure that matters. But the more general SBI techniques, they don't require you to specify fiducial cosmology. They're mapping the either posterior directly or the joint distribution. So that's not a problem.
okay, thank you.
Perfect.
Expect the 1,000 simulations number will change when you change certain things about the observations, such as like how non-Gaussian it is, or is it the volume?
So I kind of glossed over this detail in the talk, but the posterior comparison that I was showing was with the compressed power spectrum. So in that sense, as long as the dimensionality of the problem doesn't change, I think the performance will be relatively similar. But if the dimensionality increases, I imagine if you're trying to estimate a conditional distribution with the full bispectrum of like 2,000 dimensions, it's not going to work as well. But that would be my guess.
Thank you, Chan. Any other quick question? If not, thank you very much, Chan, again, and let's go on. Okay, I think. Yeah, so Ben Horowitz, right?
Ah, hello. Can you hear me?
So can you share your screen?
Yes. Okay. Can everybody see my? Oh, there.
Yes.
I can see my slides because I see the video. Hello, everybody. Hello, everybody. I'm Ben Horowitz. I'm a postdoc at Princeton. Said I can't be there in person. I'm currently stuck.
Ben, sorry.
Yeah.
We are wondering if we can see your face.
Oh, let me try to do that as well. 1 sec. Oh, can you see me?
Very nice.
Okay. Oh, okay. everything good?
Perfect now. Thank you. Thank you, Ben.
Hello, everybody. I'm Ben Hortz. I'm a postdoc at Princeton University, and I'm sad I can't be there in person. I'm currently stuck out in smoky California. So today I'm going to be talking about some recently posted and archived work with some collaborators at Lawrence Berkeley National Lab, looking at surrogate models for cosmological hydrodynamical simulations. So what we're going to be looking at today is essentially mapping from dark matter only simulation to a full hydrodynamical simulation. And the hydrodynamical simulation we're going to be using for this analysis is the NIX simulation, which perhaps people who don't work in Lyman alpha forest might be a little bit less familiar with, but it's a hydrodynamical simulation that does the full differential equations on the grid, a full AMRX style hydrodynamical simulation. And compared to a dark matter only simulation, you have certainly a lot more computational expense. So not only do you have to solve all these differential equations to study your baryon species, to map your baryon densities and temperatures, but also you have, for a hydrodynamical simulation, higher time step requirements. You can't do things quite as coarsely as you would for a dark matter only simulation. And then you also have to do all the mapping of the actual atomic species and Doppler shifts and things like that for the full hydrodynamics. So if we're able to instead construct a surrogate model that maps from dark matter only simulations to full hydrodynamics, we would really cut down the computational expenses for a lot of mock generation for next generation surveys, as well as we could embed it within a forward modeling framework to map from the dark matter to hydrodynamics to do things like initial density reconstructions. So that's kind of the goal for today. Now, the example I'll be kind of focusing on is Lyman alpha forest flux. And what's nice about Lyman alpha forest flux is that because we can use these coarser simulations in terms of not having things like AGN feedback or star formation processes, because those don't affect the Lyman alpha forest signal quite as much, at least for things like DESI. So the particular framework we'll be using here is, rather than mapping directly to the Lyman alpha forest flux, we'll instead map to the actual core outputs of hydrodynamical simulations. So the baryon density, the baryon temperature, and the baryon velocities. And the reason why we don't map, say, directly to Lyman alpha forest flux is a few reasons. First, the mapping to Lyman alpha forest flux is actually in some ways a little bit more complicated than the mapping to these quantities listed here, because you have redshift-based distortions when you actually go to the full Lyman alpha forest signal. And so the mapping becomes inherently less local, because in abstract, if you have a high line of sight velocity, you'll have a significant redshift spacing effect. Secondly, because there's line profiles in your Lyman alpha forest signal, you'll have essentially a line of sight effect. And when you do this mapping directly to Lyman alpha forest flux, you're picking out a chosen direction. And so you're losing some rotational symmetries, which we'll use to accelerate our training. And finally, with the actual core Lyman alpha, with the core hydrodynamical outputs, you could, of course, map to things other than just Lyman alpha forest flux. So because we have a relatively easy analytical mapping from these core hydrodynamical quantities, it's just an integral along the line of sight, we might as well only have our surrogate model deal with this very complicated step and let this slightly more simple step be done with existing analytical tools. So because this is a learning the universe, a machine learning oriented conference, the way that we'll be constructing this mapping from dark matter only to full hydrodynamics is, of course, with neural networks. And this goes into a lot of recent research over the past decade on image translation models. So here is some kind of classic examples you might have seen in lots of other talks or in pop science articles, where you can use ways to go from a labeled image of, say, the facade or whatnot of a building to an actual kind of realistic picture, or these kind of models where you can take a picture and then have a neural network change the season that it's taken or change the time of day that the picture is taken. And so we'll be leveraging these types of existing tools to construct a model to do this, this mapping from dark matter to full hydrodynamics. So I'll be talking about two approaches that we've been working on. So one is a deterministic approach, which goes into the kind of standard Unet architecture with an adversarial loss to reconstruct these hydrodynamical fields. And then the kind of other approach that's a little bit more, in some ways more novel, is what I call the HYPHE approach, hydrodynamical physics variational approach, which will actually allow for uncertainty mapping within these surrogate models. So rather than just mapping to one single hydrodynamical output, we can actually map to various realistic hydrodynamical outputs that all are consistent with the input dark matter field. So for the Unet adversarial loss approach, I assume people are probably pretty familiar with Unets by now. They've showed up in a lot of different models for various astrophysical surrogate modeling in the last couple of years. But essentially, you take an input image, you apply various convolutional layers, combined with downsampling, convolutional layers, downsampling. Every time you downsample, you save a version of the field, and you pass it through these skip connections. After enough downsampling, you have a bottlenecked layer, and then you have an upsampling, and then you combine with the skip connected downsampled versions at these different scales. And so you can imagine that the Unet is essentially taking information across a range of scales to best inform the end mapping. And so we'll use this architecture to map from the dark matter to the hydrodynamical physics. For the actual training, because we again kept the rotational symmetries of the problem, we can exploit those to accelerate our training to generate additional rotated versions of our field. The first thing we tried was using just an L1 loss, kind of the most naive thing, to compare the output dark matter field or output reconstructed hydrodynamical field to the true hydrodynamical field in that corresponding simulation. But just using an L1 loss, it has some well-known issues. In particular, it smooths out a lot of the fine scale features. So here's another example from the machine learning literature where people try to do this mapping for a city scene with just an L1 loss, and it turns into this blurry kind of image you see on the left. And so the way people have been using to correct for this is using an adversarial loss to basically train a separate model to try and differentiate between the reconstructed image and the true image. And basically you try to fool that adversarial network. And with these adversarial losses, you can get really great image reconstruction quality. But the issue for all those who've tried to train adversarial losses is they're really, really hard to train. And your parameter space for the network parameters really explodes. You have to train so many additional free parameters to do this kind of mapping. And so one kind of trick we came up with to accelerate this process and make it a little bit more computationally feasible, particularly when dealing with these really, really huge three-dimensional images that are these hydrodynamical simulations, is to actually truncate the field in Fourier space. So essentially, if we take hydrodynamical simulated images, we take the Fourier transform of them, we truncate the upper half of the wave numbers, because it's in 3 dimensions, you're truncating basically by a factor of 8. You can still get the same quality image in the end with the truncated fields, but when you calculate summary statistics, you actually go to the mapping to line alpha force flux, you still get the same line alpha force flux. So this really reduces the dimensionality of the problem and allows us to use these kinds of adversarial techniques in these very high dimensional image spaces. So to kind of show the reconstructed qualities in these cases, here you can see the input dark matter fields and dark matter velocity fields, as well as the predicted fields. Kind of by eye, you can see it already traces similar structures. you could kind of zoom in on different areas and see slightly better, slightly worse reconstructions by eye. But when we actually go to summary statistics, like those describing the Lyman alpha force power spectra, or the Lyman alpha force flux PDF, you can see extremely accurate reconstructions across a range of scales. If I compare against fluctuating Gunn-Peterson approximation, kind of our best attempt to create a surrogate model just with a simple semi-analytical formula. But you can see we can really get within a 1 or 2% accuracy across the range that would be probed by, say, DESI or any other next generation Lyman alpha forest experiment. So we're kind of happy with these results. But when we try to see where kind of the pathological cases where the model really breaks down, if you want to try to use this tool for some other astrophysical observable, Lyman alpha forest flux is kind of somewhat easy. But when you actually look at the temperature field itself, you can see that there's some real anomalies. So for example, here's kind of the most pathological example, which are the large scale astrophysical shocks. So when you look at just the dark matter distribution, there's no real sign that you'd see these big shocks. They don't really show up in the dark matter field. There's not really certain configurations of dark matter that are 100% certain to give you a shock-like feature. But then when you look at, of course, the velocity fields or the temperature fields, they really become quite apparent. This is kind of a large shock in the box, but you can even see it on smaller scales. And it's unsurprising that this Unet architecture that we kind of showed is unable to capture these kinds of astrophysical shocks because they are rare events, and there's nothing inherently stochastic about our model, which would allow the network to just learn, hey, there's some certain probability of a shock being at this point. So that will inspire part 2 of this short talk, which is actually including a variational aspect to the approach and introducing a latent space that we would then marginalize out for whatever our downstream task is. So here, to kind of put that in formula, our target distribution is essentially our probability of a given hydrodynamical field conditioned on a dark matter field. And what we'll be doing is introducing a latent space to capture the uncertainty in this mapping, and we will marginalize over this space. And so the particular architecture that is really naturally used in these kinds of cases is a variational autoencoder. I, again, kind of assume people are relatively familiar with this, but the essential idea is you take in your input image, you map to some region of a latent space characterized by means and standard deviations. You then sample from that latent space, and then you have a decoder which will map that latent space into the image space. And you can then compare the reconstructed image with the input image and have a loss based on both how well these two match, as well as based on the characteristics of the latent space you want to essentially kind of impose. And so the kind of addition to this network that we're going to be using is trying to basically include this conditional mapping within the variational autoencoder, as well as include this Unet architecture, which we kind of saw from the previous work is really successful. So here's kind of the fancy diagram to show off. It's really fancy, so you know it must be right. We have a variational autoencoder essentially for the hydrodynamical field. So here's the true hydrodynamical field that goes through all these convolutional layers, gets combined, and then the same variational step gets decoded to the hydrodynamical field. But we want this mapping to be conditioned on our dark matter fields. And in the end, we want our variational latent space to not depend on the specifics of the hydrodynamical field, but instead to be about all the mappings between the dark matter field and the hydrodynamical field. And so hence we include this the dark matter field in the same downsampling type approach, constantly exchanging information with the hydrodynamical encoder. And so when we actually want to do the end mapping for our actual test dark matter boxes, we can essentially cut out the hydrodynamical field entirely, just perform this downsampling, sample the latent space just as in the standard variational autoencoder, and generate realistic hydrodynamical fields. So here's just showing the output from those mappings in our different hydrodynamical quantities. You can see we construct this little shock feature quite well in this one sample, and then we can actually perform a full sampling over the latent space to get realistic hydrodynamical fields, realistic temperature fields that seem to actually capture the uncertainty in the mapping. For example, where there's the shock feature, you can see a lot of uncertainty in the latent space samples, but where the hydrodynamics is relatively simple, say in this like lower third of the panel, you can see there's very little variation in our samples, showing that our network is actually able to capture this uncertainty. And you can generate variance maps based on this and use those in your downstream task. And so here we show just a kind of trying to make this more quantified to see, is our variance really an accurate representation of our variance? And do we end up with an unbiased estimate for the temperature? And so here's a pixel by pixel comparison where we look at the variance of each pixel. We look at the mean of the reconstructed minus the true temperature value. And we would expect this to follow a roughly Gaussian distribution, which it seems to. We do have these tails about somebody who's better at training neural networks than me can maybe make a network that's even able to better capture these really extreme temperature values. But for a lot of the downstream analysis tasks, we think this is a great addition to the neural network model, and capturing these variances is very important. So I think I'm running short on time, but just to quickly summarize and to show we can also get the right temperature density relationships from these types of models, which is something that the deterministic approach is not able to do, as well as get comparable results in the power spectra. So I guess I'll leave up my summary and take any questions people might have.
Thank you, Ben. I think we only have time for one quick question. Yes, please, Nav.
Hi, I was wondering what's the simulation box size you took?
So for the training boxes, we trained on 2.5 MPC cubed boxes. For all the downstream analysis tasks, like for example, calculating these power spectra or calculating these temperature density relationships, we use a full mixed box size, which I believe is 15 MPC. I guess I could actually show
okay, so
it's like 20 MPC.
Okay, so you like basically focused on the very non-linear scales, like extremely small.
This is very much focused on the small scales. The idea is that because we're looking at the mapping from dark matter to hydrodynamics, for the most part, the hydrodynamical properties are fairly local. In certain cases, for example, if you're looking at like fluctuating UV backgrounds or kind of reionization models, things like that, you might expect larger scale correlations. But essentially we're here kind of assuming that the dark matter field will capture all those long scale correlations for us. So all we care about is those really small scale mapping.
Okay, thank you.
So I think Shirley told me that we have a little bit more time. So Vanessa, please.
Hi, Ben. Vanessa here. I was wondering if you had checked the accuracy of your variational posterior, because I know that this is sometimes a problem with VEs, that they actually get the posterior wrong.
So, meaning, I guess, what type
if you sampled the posterior, it would look different to the Gaussian approximation that the variational approximation is.
So one thing we did to check this, and maybe this is not quite getting at your answer, is looking at the image of our samples in the latent space. And we did find those very closely followed a Gaussian. And when we broke it up into like high density environments and low density environments and different types of cosmic structures, we found the image of the samples in the latent space followed very closely a unit normal Gaussian, which is what we ended up sampling for like this kind of image here. I don't know if that, they're kind of talking about like a structure in the latent space. Or are you talking
what was your latent space dimensionality again?
This was, we used 27-dimensional latent space.
So you could, in principle, also sample the posterior maybe and just like do a direct comparison. 27 is maybe.
So are you talking about like kind of looking at these samples here and then saying use
those?
Yeah,
like sampling the actual posterior, right? Here you're sampling the variational posterior, or are you sampling the actual posterior?
Sampling the variational posterior or the apple. Okay. I guess it's unclear to me what you would do with the actual, because it's very hard to know what the actual posterior.
Well, you have a likelihood, right? Your VE gives you a likelihood and it gives you a prior. So you can construct a posterior, right? And sample from the actual posterior, which is going to be different from the mean field. I guess you made a mean field approximation.
Yeah, I guess what kind of works out well is that in the end, they do end up being the same thing in the latent space. Because we do find that we get for a given sample, we find that the predicted means and standard deviations for a given sample, once we fully train our model, follow exactly a unit normal Gaussian, which is very nice. I remember there was a paper, I believe was it you and Francois, that was looking at like a normalizing flow on top of that, or maybe that was just to the latent space to, so it definitely makes a lot of sense where once to train the model, if we're not getting a unit normal Gaussian there, to apply those kind of normalizing flows. I was all ready to apply that.
That was on the prior, right? So there's prior and posterior, right?
I see. Yeah.
Okay.
Yeah, no, I'd be interested in talking with you more about it.
Yeah,
later.
let's chat offline maybe. Yeah.
Very curious to hear more.
Yes, please.
Hi, Ben. Super nice talk. Thank you so much. I just wanted to ask you very quickly. So you mentioned that you plan to apply this to stochastic processes such as AGN and galaxies. What do you foresee are going to be the biggest issues?
Which I see will be the biggest issues. So I think already it seems like the model is able to capture pretty well stochastic processes. I think it'll take a lot of tuning of the latent space structure to really be able to capture well these stochastic processes. So we might have to radically increase the latent space dimensionality, which could cause a lot of issues with training. And that's where I probably see as the most difficult trying to capture these stochastic processes. Right now, Lyman alpha forest itself is kind of nice because it's not super affected by stochastic processes, even these shocks. So we kind of have a lot of wiggle room there. But once you really try to say, oh, I want the exact same effective AGN feedback or the exact same star formation processes, I think that'll be very hard to actually well train the model to do.
Yeah, thank you so much.
Any other question? If not, thank you, Ben, again for the beautiful talk.
Yeah.
Okay, so who is next? Jay, don't leave. Take your time, take your time.
Do I have a pointer? On this one, I mean, we have a physical one. Okay. Can go ahead?
Yes, please, Jay.
I can remove my mask. Yeah, I have 4 vaccine shots, so don't worry about it.
4 vaccine?
I got 2 in India and it wasn't recognized here. Anyway, we can talk later about it. Yeah. So, hi, I'm Jay Wadekar. I'm a finishing PhD student at NYU, going to join as a postdoc at the IIS this fall. And today I'll talk about cluster mass estimation with symbolic regression. And this is work done with Leander and Paco at Princeton. Colin at Columbia, David Shirley at CCA, and Miles has recently joined from Princeton. How do I? Okay, thanks. Sorry, I'm like old school. So okay, let me give a brief background of like why cluster mass estimation is important for cosmology. So what I mean by clusters is like these are one of the largest objects in the universe. These have tens to hundreds of galaxies, have masses of around 10 to the 14 to 10 to the 15 solar masses, and their number density is exponentially sensitive to cosmology. So here I've shown like two examples where you have for different cosmologies, you can see that the abundance of clusters as a function of redshift is like sensitively dependent on them. And actually, one interesting thing to mention is like Fritz Zwicky observed made estimates of how much unseen matter there was in the universe using a coma cluster. So clusters were used for one of the first predictions for dark matter in the universe. And I think it is an interesting time for cluster cosmology because we'll observe clusters in the universe in many wavelengths. So we'll have optical, radio, microwave, X-ray, lensing, and we would have a lot of data from all these surveys. So we want to think about like ways which we can extract complementary information from these different surveys, and so can we use that to make accurate cosmological predictions from clusters? So let me talk about what are the traditional approaches that are used for estimating masses of clusters. So like for example, for an optical survey, you observe like positions of galaxies in the clusters, and you also have estimate for the velocities. So you can calculate like a single property, let's say the velocity dispersion. From microwave surveys, you can also calculate like one property, which is the total electron pressure. And we have theoretical intuition from things such as virial theorem that these properties should have a power law dependence on the cluster mass. And so we measure like one single property for clusters and then determine the mass from this power law relation. And you can see that from simulations, we can estimate what the scatter is in these relations. And so the predictions that we make have some error depending on this scatter. But let me emphasize that in traditional approaches, we reduce all the data from the clusters to a single data point, which is either the velocity dispersion or the electron pressure or something similar. But then with these machine learning tools, we are not limited to only using like a single data point. We can actually use a lot more data to do this analysis. So we can use, let's say, the histogram of the velocities of galaxies in the cluster, or we can also use like the 3D positions of galaxies in this cluster to make this estimate of the cluster mass. You can also combine different wavelengths, which is what I've shown here. You can use a machine learning model here and combine these multi-wavelength data to again or estimate cluster masses more accurately. And to emphasize that this is, I think, a recently interesting field to determine masses of clusters. I've shown like some recent work on this. But then, so the approach that we are working on is using symbolic regression. And I think there is a trade-off in the approaches used in machine learning community, where you have deep neural networks, which can work on data which has a big dimension. So these can work on 2D, like large images or 3D boxes. And also you can have data with a large input size. But then in terms of interpretability, it's very hard to interpret what these networks are learning. And also there becomes a question, so we train these networks on simulations, and would they generalize to real data where you have noise or systematics? And so in this work, we'll try to go towards the left, use a symbolic regression, where you can feed it like these data points and it can output functional forms which like fit to this data. So one thing to keep in mind here is that for symbolic regression, we can only use this on inputs which are like low dimensional, and also the data size has to also be small. So you can use this like ballpark on inputs with 10 dimensions and data size of around like 10,000 points, let's say. So the goal of our project was estimating cluster mass as a function of this YCMB. So I'll refer to this, the total electron pressure in a halo as Y throughout this talk. And what we want to do is, can we find some complementary information in X-ray surveys or galaxy surveys, which we can use with this estimate of Y, and then make or predict the cluster masses more accurately. And the problem here is for symbolic regression is that we can think of like many parameters in X-ray or galaxy surveys. I've listed some which can be important, and so we need to first determine which one of them like has an effect on the cluster mass prediction. So we have to narrow down our parameter space first, and so that's what we did using a random forest regressor. We first found out like which parameters are more important, and so these are the two ones we found were impacting the cluster mass estimates. And so then we'll add this to the symbolic regressor, and we have used this Pyser package. I don't know if Miles is here, but this was written by Miles. Yeah, and I think in his talk he might talk about this like in more detail. Okay, let me then directly jump to our results. So on the top panel, I'm showing the traditional way of estimating cluster masses, where you measure the Y parameter, which is this integrated electron pressure, and then you have how you have this power law dependence. And so you can see that there is a scatter. And if we include, what we found was that if we include one observable from X-ray surveys, which is this concentration of gas, which is I've shown in the second panel, we actually get reduced scatter. And this is important because in the end, our constraints on cosmology will be sensitive to how much scatter we have in our mass prediction. So after we got this equation, we then went back and checked that actually one of the reasons was that the central profiles of clusters are noisier. And what this equation is doing is basically it's upweighting the outer parts of the cluster and downweighting the central part. And so we thought this was interesting. But then these results were on Illustris TNG. So TNG has only one configuration of baryonic feedback, as most people would know. And it also is just based on one initial conditions. And so would our results hold in more general setting? And we thought like we had some theoretical intuition of why we were getting these results. So we were interested in checking this. And so an ideal data set, which I think Paco would talk about on Wednesday, I think, would be these camel simulations. So where we tested our results. And so let me show like our results for camels. So here you have the Simba simulations in camels, and these have different baryonic feedback implementations as compared to TNG. And also these simulations have different initial seeds. And it was like interesting to see that our results still hold for when we do this check. And you can see that you can get a reduction in scatter in both these cases. So apart from reducing scatter at high halo masses, it is also important to correct this deviation from the power law that you see at for low halo masses, as these low halo mass clusters can be important for astrophysics. So this was like the part 2 of our work, and this is actually happening because AGN or supernova feedback can eject gas out of the cluster, and so it no longer follows this power law, which is based on virial theorem. And so we were thinking whether we can also use these techniques for correcting these deviations. And so let me show like some of our preliminary results. If you like introduce this stellar mass over gas mass ratio into the y parameter, we found that you can reduce this this deviation for like low halo masses like quite significantly, so around a factor of 2. And we are like working more on like even improving these results for low halo masses. But it is interesting that yeah, you can have these simple additions you can do to some observables and get like low scatter or low deviations from your theoretical results. Okay, so I mean, I've talked about using symbolic regression for this cluster mass problem. So I think this is just one application. But in astrophysics, we have a lot of scaling relations that we use. And I think symbolic regression is like a promising technique to also use on like these areas. And so some of the areas that I personally have worked on is for like finding number of galaxies or neutral hydrogen content. So I think like people here would be familiar. We use this HOD relations where you say that the number of galaxies in the halo is a function of halo mass only, and then make galaxy catalogs. But then as our surveys improve, we want more precision, catalogs with higher precision. And so we should include like effects beyond the halo mass. And so it becomes a similar question: what effects are important? What functional form should we use to combine them? And I think symbolic regression is an interesting like method for this. And I think Anna Maria will be talking about this problem of like number of galaxies in a halo as a function of halo mass. I won't go into the equations, I think. And with Paco, Shirley, and Lawrence, we also worked on a similar problem where you find the neutral hydrogen content of a halo as a function of halo mass and other properties. Okay, so let me summarize. So my first point in this talk was to motivate that machine learning is a promising tool for multi-wavelength cluster mass estimation. We'll get data from many wavelengths by observing the universe in multiple wavelengths, and we need these techniques to combine this and more accurately predict cosmology or astrophysics. The second point I made was symbolic regression can be used to increase precision of astrophysical scaling relations. And I think this is a general tool. We use simplistic scaling relations in a lot of fields in astrophysics, like simple power laws. And I think these can be used to find interesting augmentations. And in our project, we found that it reduces scatter by 20 to 30% for high halo masses, and including like a stellar to gas mass ratio, it reduces deviation by a factor of 2 for low halo masses. So we thought this was interesting. And okay, I'm just showing again the results for these Simba simulations.
Thank you, Jay. Thank you. Questions for Jay? Yeah, many of them. Let's see. Chan.
Hi, Jay. I had a question about when you were showing the results of Camel's Simba and Camel's TNG. I noticed that the coefficients that you have are different. Are they dramatic? Are they significantly different? And if so, how do you know which one to use for when you're actually applying this to observations?
Right. Yeah, this is the question we are like currently thinking about. So one interesting thing was the coefficients we found for TNG camels was the same as what we found for the TNG simulation itself. Like, but then indeed the coefficient for camels is different, and this is a parameter like we are thinking about, like how can we get an estimate of this? We think like this relates to where you have like a break from power law, and if you can maybe measure that break from power law in observations, then you can like tune this parameter and you would have an idea. So currently we are like saying that I think these relations would hold qualitatively, but then we have to tune this one parameter based on like some other observables, I think. But we are thinking about this, sorry.
Let me first ask a question from Zoom, people in Zoom. So there is a question from San. Do you use the random forest for feature importance to identify the relevant features for your symbolic regression?
Yeah, that's a good point. So yeah, it is an important thing you can infer from random forest. So you get these relative importance of features, but then we found these are okay to like some precision, but it's not like super accurate. Sometimes we found that symbolic regression can find even more like concise estimates by something which the random forest does not show up in feature importances. So it's accurate up to an extent, and we can what I think is a way is like we can try using the symbolic regression multiple times on the say the top 5 features you get and see whether you get any interesting results.
Case.
Like when we're trying to get like some scaling relation, we usually want to apply that on all scale, right? We don't want to just a scaling relation in, you know, like a super small domain. So have you tested the scaling relation that you get out of your data on like a scale that's slightly outside your domain of training? Or like if you can, you know, of course you want to test it on all scale, but like how does that scale outside the scale that you have training on?
Yeah, so that's also a good point. So right now, I mean, at least for the high cluster masses, we are limited by the data points that we have. And for so in cosmology, like for cluster cosmology, actually people tend to use clusters above 10 to the 14, like ballpark above 10 to the 14 for these estimates, because the lower mass clusters are very noisy to do these precise estimates. So that's like the lower edge we have to think about. Like so we have checked like nearly 10 to the 14 and above that these work, and for these lower mass clusters the problem becomes different. Then the problem becomes like reducing this deviation from self similarity. So it's a different ball game. The high mass is for cosmology, the low mass is for astrophysical observations, and so we have that's why we have like tuned these two regimes separately. But and one thing also to emphasize is I think this symbolic regression is very interesting because like when we go towards high cluster masses, it's very hard to make these clusters in simulations, and we have few data points. So I think like using say like deep neural networks might be hard because we need a lot of data for training them. But here this might be a very efficient method which can generalize to these clusters with high masses. And also, so one other point was that, so why would this generalize above 10 to the 15? I think like then having some theoretical intuition why these formulae that we are getting, why are they like accurate? Is there like some physical reasoning behind them? And so that is, I think, essential to think about why this would generalize. And what we found was the one I mentioned here, the central profiles are noisier and you can downweight them using these relations.
Let's see, Nera.
So how many samples did you use for your analysis?
So for high mass clusters, I think the region I've shown in this slide, it may be like 500 clusters, and that is one limiting factor. Like we only have around so I think around like 5 times 10 to the 13. So ballpark you can say like okay 500 to 700 clusters in our analysis total.
So how sensitive is this technique to the amount of data? Let's say that you increase the data tenfold. Will the results get better?
Yeah, I mean, so this would be an important check to do in these next generation of simulations which will be coming. So there are these Millennium TNG simulations which will have like 15 times or even like some 50 times, I think, more volume than a TNG. And so it will be important to check this. But the thing we checked was we trained it on this Illustris TNG and we checked it on a different version altogether, which is these camel simulations. And it was interesting that these generalized even to those non-trivial setting where you have all these Biryani parameters like, significantly different. And so I mean there is this thing like simple things generalize better, but I don't know. I mean you can't prove this, I guess, but this is what we find in physics. Like we find this simple formulae which can be applied to many situations and hold in many different contexts. So,
okay, thank you.
Let's see one there over there. Yeah, please.
Yeah, thank you, Jay. Another question that I have is did you check whether the scattering changes when you look at different halo mass measures? So for example, M500C versus M200C. And the other thing is, do you know whether what the secondary parameters that determine the scattering are? Have you looked at any of these? Maybe that's part of the random forest test, like the environments or anything like that.
Right. Okay. So the first question was wait. Sorry. Can you say the first question?
Sure. Just if you looked at M200C versus M500C.
Yeah. So that's an interesting point. So different surveys, I think, will need different measurements. So I know, like, future CMBs might prefer the M200C scalings. So it depends on the resolution of your survey and like how wide can you observe. X-rays, the X-ray surveys prefer M500C, and we did like some estimates for M500C, and these results like seem to hold. So, but I mean, if like a different set of surveys have different requirements, we can, I think, do our test again for those cases. Yeah. And then your second question was about other secondary parameters that we found. Okay, so there were these. I mean, in the random forest, like, it also highlighted like stellar mass being important, but then in symbolic regression, like all the parameters you put in, it does not like use all of them. Sometimes it sees that one of them is like super important and it just uses that in the prediction. And so it did not like have any simple form for the stellar mass. So maybe stellar mass is important, but it enters in a very complex way, and that's why it doesn't give. It doesn't show up in the result. So one other thing to mention was this symbolic regression. It also prefers concise equations over like long equations, and so it was interesting that it just used this simple addition.
Any DW, please.
I have a quick question about, so you list a bunch of other projects that use a CNN. How does a scatter compare to the CNN approach compared to, yeah?
So you're talking about like comparison of doing these estimates using machine learning as compared to?
Yeah, compared to the convolutional neural net type, how does the scatter, have you compared the scatter you get from the symbolic regression to what you can do in the CNN? Or
okay. We haven't actually, yeah, we did some small estimates with Paco, I think, where you can use the same data set on like CNN. You can just use these properties and see. I think the results were similar to random forest. We could not find much difference.
Question before the break? Yeah, last one there.
Hi, nice talk. I just wonder, like, how are the synthetic observation compared with the real observation, like the two, like the Simba and the TNG you mentioned?
So yeah, I mean, that's an interesting question. So actually in this space, I think the observations currently favor the Simba type of feedback, where you have the mass of the halos that you think are affected by AGN feedback. So I mean, there is of course like a lot more work to be done, like to get these simulations to converge and to see like what would be the optimal configuration. But to what we should do in our projects, I think, is to use our methods on multiple simulations, and so these represent, I think, the spread into which these baryonic feedback parameters might vary, and we should check whether our methods are robust to this spread, and so can be applied to real data. But then if the real data is completely different from what simulations we have used, so then we can't say much. But that is this is the best I think we can do right now.
Okay, thank